This is a pretty controversial question from the AP exam several years ago, not only because it's titled calculus, AP calculus, sorry, cracks me up. Anyway, pretty controversial question from a couple of years ago, because specifically the question never asked anyone to find a particular solution. It referenced the particular solution several times, but it never actually required that it be found, and this very much threw people off. So if you look at the original equation, it's a differential equation. You get the dy dx and all of that. But notice it's 2x minus y. There's no product there, there's no quotient, that sort of thing. And that kind of caught people off guard because people thought, well, what do I do? Add y to both sides? That sort of thing. And the point was they never asked anyone to separate variables or to solve for the particular solution. The question just references it. So anyway, first part of the question asks the person taking the exam to find a slope field. Hopefully at this point you have a concept of what a slope field is. I'm not going to do an entire slope field here, but your function is dy dx is equal to 2x minus y. Basically at a particular point, for example, if I have the point 1, 1, for example, x is 1, y is 1, I can substitute x and y in. If x is 1 and y is 1, I get 2 minus 1 is 1. Dy dx is a slope. And so you make a little tick mark there that has a slope of approximately 1, and that represents how the graph would bend if it passed through that particular point. A slope field is really showing how a graph would be sloped, because again, when you have a dy dx equation, you just have slopes. You don't have the original function. And so if I look at the point 2 comma 1, for example, that would be an x value of 2, and that would be a y value of 1, and that's 4 minus 1, which is 3. And so at the point 2, 1, I would plot a point with a slope of 3, which is going to be steeper than a slope of 1. And anyway, when you get a whole bunch of these, you can kind of trace through, if you're given a particular point that the function passes through, you can trace through and you can get an idea of what the graph shape would look like based off the way that it curves at various points. Anyway, I'm not going to do all of that because that would be pretty time consuming, but I do want to take a look at part 2. Part 2 says to find the second derivative in terms of x and y, then use that to determine the concavity of all solution curves for the given differential equation in quadrant 2. Then it asks you to give a reason for your answer. So the primary part here is finding the second derivative. The mistake that people made on this was they thought they needed the particular solution, and you don't. You already have the first derivative. So all you need to do is take the derivative of dy dx, and this is something that they've asked pretty often on the AP exam anyway. Probably every other year or so they ask you for a second derivative and then do some analysis using the second derivative. So again, if we look at the function here, it's dy dx equals 2x minus y. I need to take the derivative of that to get the second derivative, okay? And of course the second derivative is d squared y dx squared. And notice there it's just a difference, but I have to take the derivative with respect to x, and you notice I have a y value here. So I am going to have to use implicit differentiation here. Be careful, a lot of these you have a product, and you may have to apply the product rule, but we don't in this particular case, and that actually made this aspect of the problem a little bit easier. So you can take the derivative of 2x with respect to x, and that derivative is 2. If you want to, you could say 2 times the derivative of the inside function with respect to x, which would be dx dx if you're taking the derivative implicitly. And in the second part, you're taking the derivative of y with respect to x. So the derivative of y is 1 with respect to x would be 1 dy dx, derivative of y with respect to x. And of course dx dx is really just 1. In fact, a lot of people don't even write that when they're doing the problem. So you end up with the second derivative being equal to 2 minus dy dx. Now if you go back and read the original question, you'll see they ask you to write the second derivative in terms of x and y. Okay, so you notice here I have minus dy dx. Really I can take 2 minus the original dy dx equation, which was 2x minus y. I can substitute that in place of dy dx. So make sure you have parentheses there. 2x minus y is going to go in place of the dy dx. You can simplify it or not. If you want to simplify it, you could say that d squared y dx squared is equal to 2 minus 2x plus y, if you really want to. And it asks you to find the concavity of all solution curves in quadrant 2. Okay? So what it's implying is for any point in quadrant 2, you're going to have the same concavity. And remember, concavity is based off the sign of the second derivative. If it's a positive second derivative, the concavity is concave up. If it's a negative second derivative, it's concave down. So this is really implying that all points in the second quadrant for the function will have the same concavity, which means really you could just pick a point and try and you would get the right answer. I don't think that's really a good justification as a proof. They want a reason for your answer, and just say, well, it worked for one and you said there was one answer. Not a great justification. But if you think about signs, remember we care about signs. Think about signs of values in the second quadrant. The x values are all going to be negative. The y values here are all going to be positive. If you go back and look at the original equation, if the x's are negative, you're taking a negative times a negative, and a negative times a negative x will end up being a positive value. And then y is positive. So you have 2 plus a value plus another value, which of course is going to be positive, which means you have something that's concave up. And again, you should write that up and explain that, but that's the basic idea. Okay. Part C, if you go back and read Part C talks about a particular solution to an equation with initial condition f of 2 equals 3, and they ask if the function has a relative minimum, relative maximum, or neither at x equals 2. This is where people got in trouble because this references a particular solution, but if you notice, they never ask you to actually find the particular solution. And most people just tried to find it, and then basically they would have to check to see, is the derivative 0 at that point? Is it positive to the right? Is it negative to the left? Is it changing from negative to positive or positive to negative? That sort of thing. And of course, we don't know how to integrate a sum or a difference when you have a differential equation with a y on the right-hand side. So the point was people couldn't find that integral, and as a result, they couldn't get an answer, or so they thought. But if you go back and look at this, they just had you find a second derivative, and a lot of times there's a reason they do that. You found a positive second derivative for this function for any point in the second quadrant. And we have an equation that would allow us to find the second derivative for any particular point. Well, if you notice in Part C, they tell you that f of 2 is equal to 3. So we have a point, 2, 3. You can substitute that into the second derivative equation. X is 2, y is 3. That's going to be 2 minus 4 is negative 2, plus 3 is 1. So the second derivative is positive. Okay? And the other thing they tell you is they tell you the initial condition. You have 2, 3 there. What they're really asking you here is to use the second derivative test. And if you remember, the second derivative test basically tells you that if your derivative is 0, that means you might have a relative maximum or minimum. You can use the second derivative to determine whether or not you have a relative max, a relative min, or neither. Essentially what happens here is if you have a derivative of 0, that means that you have a function that is doing one of 3 things. Either it does this and you have a minimum value, does this and you have a maximum value, or you could have a plateau point where it briefly levels out. Okay? If you notice, the concavity here is it's neither concave up nor concave down. That's just a place where your concavity would be 0. Your second derivative would be 0. This is a place, of course, where your second derivative is negative because it's concave down, and your second derivative is positive there. So the point is, if you have a derivative of 0 and your function is concave up, that's your second derivative greater than 0, you have a minimum value. If you have a second derivative that is negative, you have a maximum value. And then, of course, if you have a second derivative that's 0, it's essentially inconclusive, probably a plateau point. But that's the kind of thing that you're looking at here. So in this particular case, notice, though, that I do need to check the first derivative, okay? It's looking like it's going to be concave up, and it's looking like it's going to be a minimum value. But if you take a look here, if you check, first of all, the original derivative at 2x minus y, we're checking at the point 2, 3, you get 4 minus 3, which is 1. The first derivative is not 0, which means this is not a place where you get a relative minimum or maximum. As a result, the answer is actually neither, because the derivative is not 0 at that point. Now, most of the time, they will give you something where the derivative is 0, and then you're doing this check. If the first derivative is 0 and the second derivative is positive, you have a relative minimum. If the second derivative is negative, you have a relative maximum. We'll look at a second differential equations question. Here we've got dy dx equals e to the y. Notice it's e to the y, not e to the x, times the function 3x squared minus 6x quantity. And they reference the particular solution here. The first part asks you to write the equation of a tangent line to the graph at the point of 1, 0. Use that tangent line to approximate f of 1.2. So one of the challenges is you've got a differential equation. You don't have the original function without finding the particular solution. Sometimes that's pretty easy to find. Sometimes it's not. But you can use a tangent line equation to estimate points near a particular value. So essentially what's happening is you've got a curve of some kind, and that's function f, which we don't know. You can say, well, I've got a point here on that curve, and if you write the equation of the tangent line, points on that tangent line are very close to points on the actual curve for values near whatever x you're looking at. So you can use tangent lines near a particular point to make an estimation of points on a curve. That's the basic idea. So anyway, part A here, you're really just writing the equation of a tangent line. I would use point slope form, y minus y1 equals m times quantity x minus x1. They give you the point 1, 0. That's the point where we're making the estimation. And again, I have no idea what the curve looks like. That's just kind of a guide diagram there. But it does tell me that my x is 1 and my y is 0. We're going to fill those in, and I just need a slope. Well, luckily, I have the differential equation here, and so I can sub in my x and y, and I can get an estimated slope. That's my dy dx value. So again, they gave me a y of 0, e to the 0 power is 1, and they gave me an x value of 1. So that's going to be 3 minus 6 is negative 3. And so that ends up being my slope there. So I can fill that in. And my final equation just becomes y, since I've got the 0 there, equals negative 3 times the quantity x minus 1. Again, you can write that in slope-intercept form if you want, or you can leave it in that form. Because they're going to ask me to make a prediction, I will go ahead and multiply that out. I don't normally do that. And that's negative 3x plus 3 ends up being my equation. They asked me to make an estimation of the value of f of 1.2, so I'm subbing 1.2 back in. You know, now that I take a look at it, I think it's actually going to be easier to sub 1.2 into the top equation, because if you notice, it's factored already. 1.2 minus 1 is just 0.2, and then negative 3 times 0.2 is just negative 0.6, and that's my value. So that's actually easier to put in there than to put 1.2 in here, although that's not particularly hard either. That's going to give you negative 6.6, which you're adding 3, or I'm sorry, negative 3.6, and then you're adding 3, and you get negative 0.6. So same difference. But sometimes the factor of 1 is actually easier to work with. So I don't usually simplify unless I actually see a particular need to do that. But that's my estimated point on the curve. Okay. They may also ask you, they don't in this particular case, but they may ask you if you have an overestimate or an underestimate. If they did that, you could look at the second derivative, which I did not find in this case. But if you had a function that was concave down, my curve here that I made up was concave down, you'd have an overestimate because the straight line would go above it and the curve would curve away from it. If your second derivative was positive, the curve would curve up above the straight line, and then it would be an underestimate. So I didn't check that in this particular problem. That's another thing they can possibly ask. last part here, and I'm guessing it's the vast majority of the points, they want me to find the particular solution here. I'm going to multiply both sides of the original equation by dx, and I'm going to divide both sides by e to the y, and that's going to give me 1 over, by the way, look at the equation here. Multiply both sides by dx. And then I'm going to, you only want to multiply and divide to move things around, so I can divide both sides by e to the y. And again, this is messy, and I should be writing this on paper. That's terrible. Anyway, let me write that here. So it's, on the left, I'm dividing by e to the y, and I have a dy left. And then on the right-hand side, I still have the 3x squared minus 6x. I multiplied both sides by dx. So now at this point, that whole thing is multiplied by dx. Okay, so I have two things that are equal. I can now take the integral. Really, on the AP exam, it wouldn't be terrible if you show the separated variables part and then separately show the integral. To save time, I'm going to go ahead and just take the integral on both sides right here as part of my work. Remember that that is e to the negative y. So if you have reciprocals, I would probably write them using negative exponents. The integral of e to the negative y is equal to the integral of the quantity 3x squared minus 6x quantity dx. The derivative of the inside function here with respect to y is negative 1. So I need a negative 1, which is really being multiplied in there. And I balance it with a negative 1 on the outside. So I get negative e to the negative y is equal to x cubed minus 3x squared plus c. Okay? Don't leave that as e to the negative e to the negative y. Multiply everything by negative 1. Write it as e to the y equals negative x cubed plus 3x squared minus c. I would do it right at that point. All right? You go back and look at the original question. They give you the point 1, 0 that it has to pass through. And so we need to get that to work out. Usually you can sub in now. These non-calculator problems are usually set up so you can solve for c as soon as you integrate. And that way you make sure you get that point. So that's going to be, if I sub 0 for y, I get e to the 0 is equal to, it's negative 1 cubed plus 3 times 1 squared minus c. And so that's going to be 1 equals negative 1 plus 3 minus c. Let's see, negative 1 plus 3 is 2. If I subtract 2 from both sides, I'm going to get negative 1 is equal to negative c. So it looks like c is going to be equal to 1 here when I solve that equation. And now I can put all this back together. I have e to the negative y is equal to negative x cubed minus 3x squared. Remember, it was minus c, so it's minus 1. All right. They do want me to find the particular solution. They specifically say I need it in y equals, or f of x equals form. So I do need to solve for y. Probably only going to be worth a point. Notice this is e to a y power. I can take the natural log of both sides. And if I take the natural log of this, natural log of e to a power, you just get the power. I have to balance it by taking the natural log of that side. So I'm going to get negative y is equal to ln of negative x cubed minus 3x squared minus 1. I can multiply both sides by negative 1, and I get a negative natural log as my final answer there. Okay, so that's my final solution now that I've solved for y. Let's take a look at the scoring guide, see what that says. Let's see, in part 1 there, you can see part 1 is 3 points. So the derivative at the point, we get a point for that. Tangent line equation, we get a point. And for the approximation, we get a point. So we got all 3 there. Second part, 6 points. 6 points for that antiderivative there. Separating variables, we get a point. The left and right side, antiderivatives, you get a point just for putting the constant of integration in there, the plus c. Testing the initial condition, you get a point. And then finally, you get a point for y.